Okay, so just a reminder, let's just recall positional multiplicity. Okay, positional multiplicity was, something that looked like this. I am only interested in where all of my molecules are located, so it could look something like this. Okay. The other thing is I could also have some different categories. Right? So I'm calculating positional multiplicity W. M is the number of spaces I have. Okay? And N sub T is equal to the number of different categories I have. Okay, and so that includes both, the blue ideal gas molecules, but if I have red ones, some other type of gas that I could distinguish, or some purple gases that I could distinguish, these other categories would be there as well. And our final category is always going to be empty spaces. And when this gets really large, when the numbers get large, we use Stirling. Okay, so the important thing to consider, though, is that these molecules also have kinetic energy and potential energy if they're not an ideal gas anymore, as soon as it's a protein running into another protein. Okay? So these molecules have kinetic energy, okay? So they're moving, and potentially, they have potential energy if it's a non-ideal gas. Okay, so these could be ideal gas, or they could be a more complex, biomolecule, like a protein. For the sake of describing energy distributions in this class, we're just going to call energy U. Okay, so that kinetic energy, we're really only going to consider kinetic energy. We won't consider potential energy. Okay. They have kinetic energy that we'll call capital U, and it's not necessarily the same for every molecule. So what was the other way to, the other definition of temperature? Temperature is a measure of what? Of average kinetic energy, okay? That is important, okay? Temperature is a relative measure of average kinetic energy. These do not all have to be at the exact same kinetic energy, okay? So we could have, tell me if I showed a figure like this before. I thought I did. So it showed something like this. It had a bunch of little lines, and it was like translational kinetic energy. And then there was bigger gaps for like rotational potential energy differences, and then maybe vibrational was bigger. Did I show a figure like that before? Yeah, on the slides. I should draw it. Okay. Well, there are different energy levels that these molecules can be in, okay? By quantum mechanics, they are quantized, they are discrete, okay? So that's why we've drawn them with this sort of gap between them. You're either in the lowest level or the next level up, okay? And this is just, I'm moving faster with velocity, getting, put in some heat, raise the temp, and now I have a little bit more kinetic energy. I might be able to move, that's fine. Rotational potential energy was, what were our examples there? We're actually doing what? First of all, to have potential energy, I have what? I'm sorry? Okay. Yes. That's not a wrong statement that if you have potential energy, then you can have the ability to do work. But thinking about an ideal gas versus something else. I have bonds. Okay? I have chemical potential energy stored in my bonds. And so I can rotate about those bonds, or we said if we actually start vibrating or stretching some of the bonds, that's going to take even more energy to get to the next level, stuff like that. Okay? I swear I showed that figure. We'll see it soon. Okay? So we can describe these energy levels, and again, this is just sort of drawing them as lines like this is a way to give us a visual, like a picture. Doesn't necessarily reflect anything other than when you get a question about energy distributions and the first thing is draw a picture. This is how you draw it. You draw lines and label your energy levels. Okay? So let's say we have some sort of, ground energy state here. And then we have some higher level, and we could have maybe 4 molecules here, 3 molecules are in this level, maybe 1 molecule's here, doesn't matter, okay? So now to do multiplicity, M is now equal to the number of molecules I have, okay? This is distinctly different from what's going on over here, okay? This was total number of spaces, this is now the number of molecules in my system. And N sub T, my categories, are now my energy levels. Okay, from 0, 1, 2, 3, this is increasing energy U. Okay. So these are my levels, 0, 1. Okay, and so when I want to, let's say, write the multiplicity for this one, what goes on the top? 8 factorial. I didn't really think about how many dots I drew. Okay? In the 0th level, I have 4. In the first level, I have 3. Next, I have 1. Any future levels are all 0. I don't need to write anything. Okay? This is fine right now. There's a small enough number of molecules that I can count them. Eventually, we're going to get to a number of molecules we can no longer count and track. And so instead, what we need is the probability of being in any given level, okay? That's what we're building towards. And keep in mind, with the ground state's always going to be given by a 0 energy. And this is where everything wants to be, right? Things want to minimize energy. Keep that in mind as we go forward. I now feel like I can't draw exclamation points to emphasize things because it just always looks like a factorial now. After a letter, I think you'll be fine, but I've done it sometimes after a number, like, the probability should sum to 1, and then I'll draw an exclamation point. I'm like, 1 factorial still is 1, but now I panic. Okay, so let's talk about some rules, some assumptions for energy distributions. Okay. Energy distributions, they describe, let's see stuff, okay. They describe the population of molecules across possible energy levels. And we have some simplifying assumptions. So the first one, 0 will just be, and originally include this one, that energy levels are quantized and discrete. Who's taken quantum mechanics? The MSc department made us take as sophomores this quantum physics class that was taught in MSc. None of us ever had a clue what was going on, pretty much ever. But we drew a lot of energy distributions. I know that was happening. I know I was exciting photons into new electron shells and stuff. Didn't end up being what I went on to do. Right? Went a little more bio with it. But. Okay, so let the energy levels be evenly spaced. Number 2, let the level, the lowest level, or ground state, is always 0. Units are arbitrary. So we have sort of arbitrary units. It could be kilojoules, or joules per mole. Maybe I'll give it to you, maybe I won't. It won't matter. Okay, you could just write energy units, depending on what information you've been given in the problem. Okay, so what this means is U sub 0 is equal to 0, U sub 1 would be equal to 1, U sub 2 is equal to 2, or it could be something like use of 0 is equal to 0, use of 1 is equal to 2, use of 2 is equal to 4, these distances are the same. Now I will say this, this is really suitable for introducing all of this stuff. Do you think evenly spaced energy levels is real life? Yeah, obviously not. And there will be an example problem on the homework where they're not evenly spaced. So just what you'll use is the energy values given to do your calculations rather than making the assumption. No molecule can occupy an energy level higher than the total energy of the system, which we're going to call U total. So if, for example, like your total energy was 4, there's no single molecule in the 5th energy level. It's just not possible. And then our 4th assumption, energy is always conserved. What is the other name for this? First law. First law of thermo, okay? And so the way to show this would be the sum over all of the levels from the ith level equal to 0 up to t number of total levels is n sub I times the energy of that level. U sub I is equal to U total. Okay. So this is the energy of the ith level. And this is the number of molecules in the ith